My name is Bahaa Saleh. I am with the University of Central Florida in the USA, and my co-authors are with Cairo University and Zewail City in Egypt. We'll present today a quantum key distribution system immune to intercept-resend attacks using fake state photons and detector control. The system supplements the familiar BB84 bidirectional Bob Alice Bob communication system with a randomizer U protecting entry into Bob's receiver. An auxiliary polarization qubit carries a changing password, which is learned upon leaving Bob's and is not available to Eve. This is facilitated by the polarization compensation action of a Faraday mirror, which compensates distortion in a round trip from Bob to Alice and back, but not compensate for Eve's entry. So here's the scheme. Begin with a laser source, creating a single photon in polarization state, H and V, which goes through an unbalanced Mach-Zehnder interferometer, changing it into time bin state. It passes through the randomizer U and its polarization changes. Then it goes through Alice, whereupon it gets phase modulated in two non-orthogonal bases. And it comes back, it goes through U, and thanks to the Faraday mirror, the distortion introduced by the randomizer is compensated for. It goes back into the Mach-Zehnder interferometer where the polarization, where the time bin state that carries the information gets changed into polarization again. Then it gets directed downward at the polarizing beam splitter. It gets downward fully. And then it is measured by Bob in two non-orthogonal bases, diagonal and circular, and gives the clicks and everything is normal. And that is the BB84. You see here that we have used 3 degrees of freedom. Polarization, initially time bin, back to polarization, and then to path. But the time bin and the polarizations were put together with the polarization really being affected by the gateway and is in fact a password that allows the message coming back from Alice to pass through, but not Eve's. So let's see what Eve might do. Well, Eve intercepts the photon coming back from Alice, and then it would have to, knowing the system, she would send, she would detect and resend the photons in the time bin state and elect some polarization that she really doesn't know that goes through the system, but because it passes through the randomizer, it is no longer directed fully in the downward path, which we call the secure path, but it can also go to the alert path up there and gives an alert that the system has been tampered with. This is the basic idea. So the study that we need to go through, aside from going through how the state is modified, allowing Eve to use a general mixed state polarization, and of course the time bin states that she has detected and modulates with a different phase, as in her attack to BB84. Now let's see what happens to the polarization as it goes through the distortion. Eve will use a blinding attack. So let's see what happens to triggering a blinded detector. A blinded detector is characterized by two thresholds. One is what is called E never. When the triggering pulse energy is below E never, blinded detectors never click. And then the other threshold is E always. When the triggering pulse energy is above E always, the blinded detector always clicks. And it can be shown that successful attack requires that the trigger pulse energy falls between E always and twice E never. You can see the reference here. So the criterion for Bob's detectors to be protected, two conditions for Eve's successful attack are listed here. Condition A, Eve wants never to click an alert detector. For that to happen, there's a condition on the energy in the trigger pulse multiplied by a probability of passing through the system should be less than E never for the alert detectors up here. That's the path A. This is the path B. So this is the threshold at the minimum blinding power received by detector A. This P is the maximum value of PA obtained over any randomization U. And PA is the probability that Eve's photons end up in the alert path A. Putting these two conditions together, merging them together, Bob must use detectors in the path A, that's the alert path, and the path B, that's the secure path, that satisfy this simple criterion, that be never for detectors in the secure path at half the blinding intensity, the blinding power, divided by E never at the blinding power in the alert detector must be greater than a half for all blinding powers that Eve might select. This condition can be illustrated as you see here. E never dependence on I for two different detectors, the alert detector and the secure detector. And the alert detector must be above half of the secure detector. This is half of the secure detector. That's one way of plotting this condition. Another way of plotting it is to plot E never as a function of I. Sorry, E never as a function of the blinding intensity for the alert detector and the secure detector. And because of the half, the slope is going to be half as much. So this yellow region is unsafe. And you'd like to work in the safe detector by selecting the detectors. Could this be done? We showed that this could indeed be done. In fact, we have plotted the thresholds for detectors that are in the market. These are thresholds E never of SPDSs for two detectors used in the Clavis 2 system by ID Quantique. They are plotted here versus the blinding power. And one is the gated case or the not gated case. And of course, you do it at I blinding, in this case, divided by 4, and in the other, divided by 8. That's a factor of 2. And it turned out that in these two cases are where the detectors are assigned alternatively between the two detectors, the alert and the secure. We've also done an experiment in which we played the role of Eve, controlling the polarization state to scan all points within the Poincare sphere before the polarization state enters Bob's. And we tested experimentally for these particular detectors that I alluded to, whether we indeed satisfy the conditions. And it turned out that for one choice, that the conditions are fully satisfied. Actually, in this case, in the experiment, the conditions A and B were met for all levels of blinding power. Then we did this plot of showing the safe region, by plotting the E trigger in the alert detector parametrically against the E trigger in the other secure detector. And the crosses that you see here in two colors are the values that turned out to be fully in the secure region. That's what we call the camouflage region. This is when the two detectors were placed, one in the secure path and the other in the alert path. You see here, we switched them around and found out that we are safe with the exception of a few points that fall in the wrong region. So we did an attack model and a security analysis with basic assumptions. Eve can introduce photons into Bob's receiver only through the polarization randomizer. She's acquainted with configuration of the system, including timing, but has no information on the random transformation U at any time. Eve interacts identically and independently with each quantum signal. She measures the pulse encoded by Alice in one of the two bases. And Eve blinds Bob's detector using non-polarized light, then sends a bright pulse encoded by her measurement outcome. The bright trigger pulse has a pure polarization state, and that is no loss of generality. Finally, we obtain this plot. Security of the system turned out to be not based on increase of the quantum bit error rate under attack. Security is verified by the non-zero alert rate over all detector control space. So here the plot shows the blinding power and the trigger pulse energy. And what is shown here is the alert rate in red and the sifted key rate. And the alert rate is higher than the sifted key rate. And we identify here the region in yellow. This is the space of trigger energies and blinding power that provide no increase in the quantum bit error rate upon the blinding attack. So our finding is that the alert rate is always higher than the sifted key rate over all ranges of blinding power. So in conclusion, we have introduced a quantum key distribution system protected against practical hacking strategies exploiting faked state light, including the detector control attacks, and more generally, the intercept-resend strategies. More information on the security analysis and other systems are in a provisional US patent and also in a paper just published in JLT. Thank you.